All right, let's get started. So last time we were in chapter 3, and we did most of chapter 3. And like I said, we went through that chapter pretty darn quickly. So, you know, if there is anything that you are not 100% clear on, feel free to come during study hall, or you can send me an email or whatever it is, so that we can get that taken care of for you. Now, we didn't talk about section 4 in chapter 3, mostly because there's a lot of stuff in section 4 that I'm not that concerned that you know. There is really just one point in section 4 that you want to make sure you know. It talks about the difference between elements and compounds. And really what it comes down to is, you can find it on the periodic table. We've got one on the wall up here. We've got one in your book. Okay, that's an element. And an element cannot be broken down without changing the properties of what it is. Okay? For example, if you have, well, let's just say gold. Okay. You got a chunk of pure gold. You can cut it in half, but you still have gold. You can keep cutting and keep cutting, and eventually you're going to get down to a piece that, well, it's too small to keep cutting. But let's imagine that you had the tools to keep cutting and keep cutting. Eventually you'll get to the point where if you cut it, it's no longer gold. Because you are splitting the nucleus of that atom. Okay. Now, that, you know, that is, you know, the whole point of getting down to the atom. If you have something up there, it's an element. Okay? And all of the atoms are the same. If you have more than one element together, that becomes a compound. Okay? So for example, hydrogen, that's an element. Oxygen, that's an element. Water is a compound. Okay? So if it's up here on the periodic table, or in the periodic table in your book, or whatever periodic table you're looking at, it is an element. It cannot be broken down by chemical means. If, however, you have 2 or more, it becomes a compound. Okay? So that's really all I wanted to make sure you understand in section 4 of chapter 3. And so we're going to move on into chapter 4 today. Okay? Now, chapter 4, we're really going to start getting into the structure of the atom. Okay? Now, section 1 talks about what we used to think. Okay, so we're not going to spend much time there because, well, nothing in section 1 is really all that accurate anymore. Okay, it talks about how in the very beginning there were only 4 elements. Okay, we have air, water, earth, and fire. obviously, none of those are up there. Okay. So those were not actual elements, but that's kind of what they have broken them down to in the early ideas. So now there was actually an ancient Greek philosopher that thought atoms existed, that you would get to the point where you could no longer split something. The name was Democritus. Unfortunately, somebody who was more respected, better known by the name of Aristotle, didn't agree with him, and so nobody else agreed with Democritus because they said, well, if Aristotle doesn't think it's true, then it can't be true. That was kind of the thing back then. Yeah,
Maybe sometimes
it can be, yes. That's why in science we like evidence rather than, oh, that person's smart, because smart people can be wrong. So, it wasn't until a scientist by the name of John Dalton, he was able to conduct an experiment that showed we have these set ratios that things have to react in, which established that, yes, atoms are there. Okay. So, let's move on into section 2. Honestly, I don't really care that you know section 1, because like I said, it's all a bunch of old stuff that didn't turn out to be really all that true until we get to John Dalton. So, section 2. This is where we're going to really start talking about the atom and what it is. Now, atoms are very, very, very small. Okay? Very, very small. It gives an example in the book to show you just how small it is. And it says, if you could take one atom and expand it to the size of an orange, so, about this big, that would essentially take an orange and to make it the same ratio of increasing size, that orange would be about the size of the Earth. Okay. Yes, very large orange. So yes, atoms, very, very, very small. Okay. But we do have some pretty advanced technology that actually can, quote unquote, see atoms. There's a picture on page 107, and it says, that's with an electron microscope. Shows the individual atoms of a fatty acid on a graphite surface. Okay. Now that is a computer-generated image. Basically, the microscope is able to see just kind of the outline, and then the computer comes back and takes that information, makes an image, adds color, and things like that. So, but yeah, we are able to see individual atoms with the right equipment. So as it says, once scientists were convinced of the existence of atoms, a new set of questions emerged. What is an atom like? Is the composition of an atom uniform throughout, or is it composed of still smaller particles? Okay. We didn't answer those questions until almost the year 1900. So the first thing that we discovered that, kind of helped us figure out what the atom was like was the electron. Okay? This is how we represent electrons, a little e with a minus sign, okay, an electron. Now we did figure that out through the use of a cathode ray tube. Okay. There's a picture of it on 107 as well. Basically, you hook up this, what's called a cathode ray tube, okay, and you run electricity across it. And we can tell that there are electrons moving between, each side where you have the electricity. So we discovered the electron. Now, that was put to use in televisions. Now, this type of modern television does not use a cathode ray tube, but if you're familiar with the older style, it's really big, deep, heavy. They're called tube TVs because it uses a cathode ray tube.
Oh, giant.
Yeah, so you've got the screen, but then it goes back behind the screen. You don't see very many of them anymore. They don't make them really anymore. Yeah, if you have one in your home, you've had it in your home for probably at least 10 years.
We got rid of it because we got a new.
Yeah.
And also the arm was kind of failing.
Yep, that's what happens. So we discovered that the electron existed. We didn't know much about it. So they start working with it, okay, and they figure out that it has a negative charge, okay, so I put the little negative sign right there. So electrons have a negative charge, and we just call it a -1. Right? It has a charge of -1. So we figured that out, and we also started to say, well, how heavy is an electron? Okay, what is the mass of an electron? And once again, we have a description of an experiment, the oil drop experiment. I don't care that you know that experiment. Okay? To be completely honest, most of this history stuff, I'm not that concerned that you remember it. Because we want to talk about the modern type, the modern idea. But we're going to just, so that you understand how we got to where we are. So, the oil drop calculates the mass of an electron at 9.1 10 to the minus 28 grams. That's really, really small. Okay. 10 to the minus 28 is a tiny, tiny number. Okay. Which actually works out. We knew the mass of a hydrogen atom, and it is about 1 over 1,840 times the mass of a hydrogen atom. Before this, the smallest thing that we knew existed was a hydrogen atom. But now we have figured out, we've experimentally determined that we have something much, much smaller. So what this does is chemists who are trying to determine, what the atom looks like, they come up with, well, we call it the plum pudding model.
Because it's kind of garbage.
Okay? Because it looks like a bowl of pudding with plums in it, essentially. So what they said is, well, we know that we have this tiny part, the electron. Okay. So we have the electron, but we know that not everything is negatively charged. So we have to have something with a positive charge, right? So that they balance each other out. We have a neutral atom. We know that there are negatively charged parts. Now we need to balance that out with positive to get to 0. So what they said is, all right, this is the atom, and it's solid, and spread evenly throughout, we have these electrons. Okay? We have these electrons. Now, obviously, somehow these electrons can come out of that solid thing, but yeah. So, that is what people figured the atom looked like. And it makes sense, you know. You would have basically the next atom there, and there, and there, and it just, you know, builds on each other like that. But that is not how we believe an atom is today. The next revolution.
It's like the weird thing with like the balls.
Ish, yeah. Ish. So, the next thing that really happened, so we have a person by the name of Rutherford.
Oh,
So he did an interesting experiment. What he did, so he took a really, really thin piece of gold foil. Okay. What he did was over here, he has a radioactive source. Okay. Now, at that point, we knew that this radioactive source would send off alpha particles, which were positively charged. Okay. And they were physical particles. And he made it so that they would hit this foil. He wanted to see what was going to happen. Okay. If the plum pudding model was correct, okay, now he knew that these alpha particles could actually pass straight through. Now they're positively charged, which means, you know, we have this electron which is negatively charged, so if it's coming through, okay, it might be pulled a little bit towards one of these electrons because positive, negative, they attract each other. Mm-hmm. And so he was doing this and was kind of expecting, so he put a basically a detector here that could see where these were hitting. And he was expecting it pretty much all be right in this area. But he started to see some getting deflected more than what he was thinking they should. And he also put his detector behind this and found that some bounced completely backwards. Now that was astounding to him. He was quoted as saying, "I would be less surprised if I were to fire a 15-inch artillery shell, so this big, about 38 centimeters, at a piece of tissue paper and it bounced back at me." Okay? So if you have a tank that fires a projectile this big at a piece of paper and it bounces off the paper, that would have been less surprising to Rutherford than that.
Okay.
So
yeah, it's totally
he was not expecting that at all. When he started analyzing this and sitting down to do the math, he realized there was only one possible way that his results could have happened that way. And that is, we get rid of the plum pudding model, okay? And now we have to have all of the positive charge in a very, very small area with the electrons surrounding it. So that means if we have our positively charged particle, okay, it comes through here, it gets deflected by that other positive charge. Or it can even come this way and get deflected like that. Now, the interesting thing is, this also sort of explains how we can get particles to move through a solid piece of foil, because this becomes empty space. So a lot of people didn't really love the fact that his new model said that solid has a lot of empty space in it. Okay? That table right there. This book right here. All atoms, according to Rutherford, are mostly empty space. People didn't like that, but his results proved it. Okay? It proved it. Now, from there, we discover what's called the proton, and then eventually the neutron. So we have these three different types of pieces that make up atoms. Okay? These two are in the nucleus, and then the electrons are around. Now, we have still refined this idea a little bit more over time. Essentially, well, we'll get to it, but essentially what happens is we have the protons and the neutrons at the center, and then instead of just electrons being randomly throughout, they have to be in specific areas. But don't worry, we'll get to that. We'll get to that. So, now, if you remember, the electron has a negative charge. The proton has a positive charge, and the neutron has no charge. There is a chart on page 114 that has some information about them, like their mass and things like that. You will notice the proton and the neutron are pretty much the same size. Okay, the neutron is very, very slightly heavier. It is so close to it, though, that we pretty much say they're the same mass. Okay. We call it the relative mass. And we say that these each have a mass, a relative mass of 1, because they're close enough to each other that that's what it is. So, okay. So that's the idea of the atom that we're going to be working with throughout this entire year. We've got the nucleus where we have protons and neutrons, and that nucleus is surrounded by electrons. So we call it the electron cloud because it is in 3 dimensions all around. We still don't know everything about the atom. We're still trying to figure it out. And honestly, as we have done more research, we figured out that protons and neutrons are actually made up of even smaller particles. So if you smash these, you can break them up into smaller pieces. But we're not really going to get into that because that's very, very complicated. All right. Now, let's talk about how we can determine what kind of element an atom is. Let's clean this up a little bit. Read those. Now, if we look at the periodic table, we will notice every single element has a number in that box with it. Okay? Starting at 1 with hydrogen, helium is 2, lithium is 3, beryllium is 4, boron is 5, carbon is 6, nitrogen is 7, oxygen is 8, fluorine is 9, neon is 10. And it goes and goes and goes all the way to oganesson, which is 118. That is called the atomic number. It's the atomic number. And what the atomic number tells us, how many protons? Okay. Which means the number of protons in an atom determines what element it is. So for example, if we look at the periodic table, carbon is element 6. Every single atom of carbon has 6 protons. If it does not have 6 protons, it is not carbon. Okay?
The last one will get 100 something.
So yes, oganesson has 118 protons. Okay? We can do that for any element there. Okay? If we look at, silver. Silver has 47 protons. Any atom in the universe with 47 protons is silver. If it does not have 47 protons, it is not silver. Okay? That holds true from element 1 to 118. Okay? So looking at the periodic table, you can tell me how many protons any given element has. So let's just try an example. How many protons do we find in aluminum? You can tell me that. 13. Very good. Okay. If you can't see that periodic table, there's one in the back of your book. Okay, let's try another one. How many protons do we find in potassium?
19.
19. Great. How many protons do we find in platinum? 78. Excellent. Okay. That makes sense, right? Okay. The atomic number is how many protons it has. And in a neutral atom, in a neutral atom, that also means that's the number of electrons. Okay? Because remember, protons are positive, so to be neutral, we have to have the same number of electrons. Now, as we go through, we will see that that doesn't always have to happen. Okay? We can have a different number of electrons than protons. In fact, sometimes we want a different number of electrons. But if it is a neutral atom, the number of protons is going to equal the number of electrons. Okay. There is an example problem that kind of goes through that same thing that we just kind of did informally. If you want to look at that, you can, but we're going to skip over it. Okay. The next thing that we want to discuss, isotopes. Now, an isotope is an interesting thing. If you notice, we've talked about these two and how many we have in atoms, but we haven't discussed the neutron yet. Now, the neutron is actually really, really important for reasons which we will get to at the end of class when we discuss nuclear chemistry. But it's in the nucleus, and it doesn't have a charge on it, but it does have mass. And the interesting thing is, so if we go back to carbon, we said every single carbon atom has 6 protons. Well, we can have different numbers of neutrons. Okay? So carbon comes in 3 main varieties. Okay? We have carbon 12, carbon 13, and carbon 14. Okay? And what these numbers represent is the mass number. Okay? The mass number we get by adding how many protons we have and how many neutrons we have. Okay? That's all it is. The mass number is how many protons you have plus how many neutrons do you have. So in carbon 12, we know that there were 6 protons. So how many neutrons are in carbon 12? 6, right? Because 6 plus 6 is 12. What about carbon 13? How many neutrons? How many neutrons? How many neutrons? 7. All right, does everyone see why? So protons plus neutrons equals the mass number. Carbon will always have 6 protons. So to get to 13, you have to have 7 neutrons. Okay. What about carbon 14? How many neutrons? 8. Okay. Now when we write these, we can write them like this. Sometimes you'll see them like that. Other times, the way we will see this is written like that. So this bottom number tells you how many protons. It's not right. There we go. That looks better. So that's how many protons you have. That's how many total pieces in the nucleus. So this one. So you'll see it written both ways. This is probably a little more correct, but you'll see this as well, mostly because that's how we would say it. If you were reading a paper that had that in it, you would say carbon 12. So, anyway. This is what's called the isotope notation. So, now, if we look at the information in the periodic table one more time, another thing that you will see in this, on the one on the wall, happens to be in red numbers. The one in your book, I don't think they changed the color. Yeah, it's just black numbers. But there's a set of numbers. That is the average atomic mass. So what that means, when we look at these 3 different types of carbon, what they do is called a weighted average, okay? And they take into account how much of each isotope just naturally occurs, and they give an average so that if you were to have a sample of carbon, okay, on average, that atom is going to have a mass of 12.0108. I know that that's maybe not 100% clear right now. Okay? Don't stress about that. We will use that a lot and explain how we use that as we go through. Honestly, if you understand the concept of weighted averages, great. If not, you don't really need to know, as long as you can use the information on the periodic table. Okay. So to recap, we've established that we have atoms. Okay? We didn't always know that, but now we definitively know that we have atoms. We went through several different updates, I guess you would say, of what the atom was. And eventually, we get to the point where we know that in the center, we have protons and we have neutrons. And around the outside, we have electrons. Right? We also have gotten to the point where we have organized all of these elements according to how many protons they have. We've organized them according to how many protons they have. And the number of protons tells us what element it is. We also have established that not every single atom of every element is exactly the same. Yes, they have the same number of protons, but they can have a different number of neutrons. We have this example with carbon. In the book, they also give the example of copper. Okay? So copper, Cu, the atomic number is 29. Okay? So the two isotopes of copper both have 29 protons. But one of them has a mass of 63, and the other has a mass of 65. Now with that information, we can figure out how many neutrons there are in this. All we have to do is take 63 minus 29. So the number of neutrons in copper 63, 34. Copper 65, that's 36. Okay. Once again, isotopes are more useful in nuclear chemistry. So we won't deal much with isotopes again until the end of the year. But one thing to remember, isotopes chemically are identical. Okay. So if you're trying to separate these two isotopes of copper, you can't do it chemically because they react exactly the same because they're both copper. Now, can you separate them? Yes. For copper, is it worth separating them? No. At least, there's no real, I guess, financial benefit, I would say. If you're doing some sort of research, maybe it would be useful, but not really. I mean, you would have to be doing some very specific research. So, and then what we've done is we've taken all of these isotopes and we've averaged them out according to how common they are, and that's what gives us the atomic mass on our periodic table. Okay. Now, for carbon, I will just point out the atomic mass, the average, is that. Now, you will probably notice in your book, they round it off to that. You can use either value, just, whichever one you have in front of you. But if you notice, that's almost exactly 12. That tells us most of the carbon is going to be carbon 12. There's only a little bit that is 13 and 14. All right. Once again, does that really matter that you know that to do chemistry? Not so much right now. Okay, as long as you understand how to use the periodic table and how to read it and get that information on. So, okay. We'll just point out a couple of vocabulary pieces before we wrap up for the day. When we say a mass, what we're talking about is called an AMU, an atomic mass unit. Basically that equals one proton. One proton and one neutron are pretty much one AMU. Okay. Anytime that you need to know the difference between one AMU and the mass of a proton, you're doing some very, very, very specialized work. We will never need to know that difference in this class. Okay? So for this class, one proton and one neutron are one AMU. So So that's what we're actually putting, on the periodic table. So one atom of carbon works out to be that many atomic mass units. Okay. We will show you how to use that number in the coming weeks. Being able to read the periodic table to get that is going to be an essential skill for this class, but we will work on it. We'll practice it and all of that. All right. So that is where we're going to stop for the day. There is some time left, so as I'm sure you can guess, we have some homework.
Yeah.
So let me pull that up for you, and then you can get started on it.
Is this like an